This is the video for Westlake on-level chemistry's lecture over the individual gas laws. I know it says combined gas law on the front of the screen in front of you, but we're actually going to be looking at a bunch of individual gas laws that originate from the combined gas law. So if you know the combined gas law from your lecture yesterday or from watching the video for combined gas law, then this video or this lecture should be an absolute breeze for you. If you don't know what the combined gas law is, this one right in front of you, P1 V1 over N1 T1 equals P2 V2 over N2 T2, go back and watch the combined gas law video first, then come back to this video because it'll make a lot more sense. So the first of the four individual gas laws we're going to be talking about is called Boyles Law. Again, all the laws we talk about today are actually variants of the combined gas law. In Boyles Law, we assume that the temperature and the number of moles are constant. So because they are constant, they are eliminated because they don't change before and after, so we can scratch them out, which means Boyles Law is actually P1 V1 equals P2 times V2. We would say that it's an inverse relationship. In other words, as one of those values increases, the other one is actually going to decrease. So as your pressure would go up, so as your pressure goes up this way, your volume goes down. And the opposite is also true. If you were to go backwards with pressure, your volume will start increasing again. Just like with the combined gas law, your units, if you're using Boyles Law, can be anything as long as they're consistent. So you can use ATMs like always, or you could use millimeters mercury, or you could use kPa. Likewise, your volume can be liters, milliliters, however you want to use it. So here's our problem. 50 milliliters of a gas has a pressure of 740 millimeters of mercury when it is in a container. What would be the volume of the gas if it was at standard pressure? So let's label some stuff. We got a volume right here, 50 milliliters. Let's see, there we go. 50 milliliters. There it is. A pressure of 740 millimeters of mercury. I want to look for a new volume, so V2, if it's at a standard pressure. So standard pressure is going to be 1 atm, which that is going to be our P2. When you're working with all of these individual gas laws, you don't have to memorize each of them. You can just start with the combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Notice in this problem, I don't talk about temperature at all. We also don't talk about how much gas you have. Because I don't give you an N1 or an N2 or a T1 or a T2, you're actually allowed to assume that both of those are constant. So you can reduce your formula from P1 V1 N1 and T1 equaling P2 V2 over N2 T2 to a reduced P1 V1 equals P2 V2. Let's start plugging in some stuff. We got a volume of 50 milliliters. We don't have to convert that to liters if we don't want to, but we do need to make sure they match. So volume is going to match. When I solve for V2, it's going to come out as milliliters because it went in as milliliters. When I plug in my pressures, I have 1 millimeters of mercury and I have another one in ATM. It doesn't matter which one I use, so I could use either millimeters of mercury or ATM, but I have to use one of them. Honestly, it's going to be easier to convert your standard pressure from 1 atmosphere to 760 millimeters of mercury because you know your conversions. And from here, you can basically plug and chug. So we have a 740 millimeters of mercury times my V1, which is 50 milliliters. And that is going to equal my P2, which is 760 times V2. Divide both sides by 760 to solve for V2. My millimeters of mercury cancel each other out on both sides, so that I'm left with milliliters. So when we take this and plug it into our calculator, we should have 740 times 50. If I had a working calculator, that'd be great. 740 times 50 divided by 760, which gives me a new volume, V2, of 48.7 milliliters. Our second individual gas law is actually called Avogadro's Principle. It's a variant, or it came out due to Avogadro. And his law, or his rule, lets us relate the number of moles and volume. So we're going to keep temperature and pressure constant. So pressure goes away on both sides, and temperature goes away on both sides. So we get that V1 over N1 is equal to V2 over T2. This one is a direct relationship. When my number of moles increase, my volume increases. When my number of moles decrease, my volume decreases. Volume can still be in any units, just like we had with the combined gas law and just like we had with Boyles Law a second ago. But N does need to be in moles. You cannot use grams. This does need to be a mole-to-mole relationship. So here's our problem for Avogadro's principle. A balloon with a volume of 4 liters is known to contain 0.2 moles of gas. How many moles of gas remain if some of the gas is released? We don't know how much, but I do have a new volume of 3.25 liters. So let's kind of label some stuff a little bit just so we know what we're working with. We have a volume and a number of moles, V1 and N1. My new volume is 3.25, and I'm going to solve for my new number of moles of gas, N2. So I'm going to start with my combined gas law, P1 V1 over N1 T1 equals P2 V2 over N2 T2. And notice I don't tell you anything about pressure, so I can eliminate my pressures. And I don't tell you anything about temperature, so you can eliminate your temperatures, which leaves you V1 over N1 equals V2 over N2. My volumes are both in liters, so nothing I have to change there. My N that I have is in moles, so I don't have to convert that unit at all. So it becomes kind of a plug and chug formula. I have a V1, 4 liters. I have an N1, 0.200 moles, is equal to V2, which is 3.25 liters, over N2. Now you have to solve for N2, but it can't stay in the denominator, so I'm going to multiply both sides by N2, or you can cross multiply if that's kind of what you're more familiar with. N's cancel out there, pops up on the other side, so I'd get N2 times 4 over 0.2 is equal to 3.25. Shrink it just a little bit so we have some more room to work. And from here, now that I have N out of the denominator, now I can get it isolated, multiply both sides by 0.2, divide both sides by 4, so that I get 3.25 divided by 4 times 0.2 is going to give me my new number of moles. So 3.25 times 0.2 divided by 4 tells me that of my 0.2 moles remaining, I should have 0.163 moles left. This should kind of make sense. All of these values you can kind of check because you know this is a direct relationship. It's one on top of the other. Because my volume goes down, my numbers of moles should also go down when it is a direct relationship. And sure enough, I started with 0.2, and I'm down to 0.163. Our third gas law is called Gielo Sachs Law. It holds volume and the number of moles constant, so we can eliminate our V's. We can eliminate our N's, which gives us the law, or the formula, P1 over T1 is equal to P2 over T2. Your pressure can be in any units as long as both the pressures match, but your temperature must absolutely be in Kelvin. We've talked before about what the Kelvin scale is and why it's important. It's still important. We can't potentially divide by 0, so we have to work in Kelvin because that is a scale that doesn't have a true 0 to it. It is also a direct relationship, which means when one goes up, the other goes up as well, and when one goes down, the other goes down. This whole direct and indirect relationship thing comes about because of the relationship of those variables. If you have one on top and one on bottom, that's always a direct relationship. When they're next to each other, like you had in P1 times V1, that's your indirect. If they're next to each other, they're going to be indirect. So here's our problem. The pressure of a tank of gas is 2 atmospheres and the temperature is 40 degrees Celsius. So let's label our stuff. Here is P1. Here is T1. If the volume remains constant, what will the new pressure be if the temperature is lowered to 20 degrees Celsius? So T2, and I'm looking for a P2. We're going to start, as always, with our combined gas law. P1 V1 equals over N1 T1 equals P2 V2 over N2 T2. I don't give you any volumes, so you can scratch those out. I don't give you any number of moles, so you can scratch those out, which gives you your formula P1 over T1 equals P2 over T2. This is why having that understanding of the combined gas law is very, very helpful, because it lets you start there from the big formula and always reduce it down to a more manageable size. Our pressure's going to go in as atmosphere, so it's going to come out as atmosphere. And our temperatures do need to be converted, so we're going to convert from from Celsius to Kelvin. So our T1 gains 273 and goes from 40 to 313 Kelvin. And our T2 is going to go from 20 to 293 Kelvin. Now I can basically plug and chug. If you want to do the algebra first, you are more than welcome to do that. Just for simplicity's and consistency's sake, I'm going to keep plugging in first because I'm starting to get the feeling that that's more of what y'all are comfortable with. So 2 atm over 313 Kelvin is equal to a new pressure over T2, which is 293 Kelvin. Our pressure is in the numerator, so we can leave it up there. We don't have to try to do any fancy algebra or cross multiplication. We're just going to multiply both sides by 293 so that I get our P2 is equal to 2 atm, 2 atmospheres, times 293 Kelvin divided by 313 Kelvin. 2 times 293 divided by 313 will give you a new pressure of 1.87 atm. And again, you can always kind of double check it. This is a direct relationship. The fact that you have one on top and one on bottom tells you it's a direct relationship. When one value goes down, the other should go down. Your temperature dropped from 40 to 20. It went down. So your pressure should drop as well. You can't tell how much it dropped, but you should be able to at least tell that it went down. I started at 2. I've gone down to 1.87, so I know I did my algebra right. One last individual gas law, Charles's law. It holds pressure and number of moles constant and lets us see the relationship between temperature and volume. So I'm going to hold my pressures constant, my number of moles constant, which gives me V1 over T1 equals V2 over T2. Just like always, volume and pressure can be in any units, but temperature definitely needs to be in Kelvin. Again, this is another direct relationship because one is on top and one is on bottom. So when one goes up, the other has to go up in response. When one goes down, the other goes down as well. It's the benefit of knowing your relationships. It always gives you a way to kind of check your math. So here is our problem. At 20 degrees Celsius, the volume of a gas is 100 milliliters. What would be the volume of that same gas at 100 degrees Celsius? So I got T1, I got V1. At that temperature, I have this volume. What would be my new volume, V2, if you change your temperature instead to be 100 degrees? So we've labeled our stuff. Let's start with our combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. I don't give you anything about pressures, so you can cancel those out. I don't tell you how much gas you have, so you can cross those out, which gives you the formula V1 over T1 equals V2 over T2. You do need to convert. You don't need to change your volumes. It goes in as milliliters, so it's going to get solved in milliliters. It goes in as 1, it comes out as that same matching unit. You do need to convert your temperatures. So my T1 is going to turn from 20 degrees Celsius into 293 Kelvin. You add 273. And T2 is going to change from 100 degrees Celsius to 373 Kelvin. Again, add 273. And we're just going to plug in from there. 100 milliliters for V1 over 293 Kelvin for T1 equals my mystery V2 over 373 Kelvin. Solving for V2, we're going to multiply both sides by 373 so that I get V2 is equal to 100 milliliters times 373 Kelvin divided by 293 Kelvin. Kelvins cancel out, and that way you know you're ending with milliliters. So I have 100 times 373 divided by 293 gives me a final volume of 127.3 milliliters. And again, you can check kind of this context. My temperature increased. I have a direct relationship because I have one over another. So because my temperature increased, my volume should have increased as well. And sure enough, it did. It went from 100 up to 127.3. That's the last of our individual gas laws. Again, having that basis in the combined gas law is going to help you out immensely with these problems. It's going to save you a whole lot of time. Between that and labeling your variables and all of your numbers, you're going to be able to handle this just fine. But as always, if you do need a little bit more help or clarification, remember you can always come in and see us, and we're happy to explain it to you and walk you through and make up as many problems as we need to.